We present Scoop, a new scene flow estimation method for 3D point clouds. Given two consecutive observations of a dynamic scene depicted in red and green, our method computes the pair-point motion between the point clouds and correctly aligns them together. The method includes two parts: pure correspondence learning and direct refinement optimization. Different from previous work, we train a neural network that is focused only on learning deep point features without any flow regression, and initialize the flow according to point similarity in the learned feature space. Then, at the runtime phase, we optimize the residual flow refinement that results in a coherent and accurate flow field. These design choices enable Scoop to be trained on 2 orders of magnitude less data while substantially outperforming previous work. Please see our project page for more information. Scene flow estimation is a fundamental building block in 3D scene understanding, which allows various computer vision applications for the occurring autonomous driving revolution. For example, scene flow can assist in parsing objects within the scene according to their motion and enable their detection and tracking. It can also be used to aggregate sparse point clouds into a denser one for better shape completion, classification, and surface reconstruction. There are 3 main approaches in the literature for scene flow prediction from point clouds. A common approach is to train a regression model that takes the input point clouds and outputs the flow directly. This is an extremely challenging problem since the flow is regressed in the free 3D space. Another approach is to use correspondence learning together with refinement regression learning, which is easier than the full regression of the flow. However, the joint training of correspondence and refinement burdens the learning process and compromises the flow estimation results. The third approach involves no training data. Instead, the flow is optimized from scratch for each point cloud pair separately at the runtime. In this approach, the flow is initialized randomly for each scene, which results in a long optimization time. In contrast to previous work, we propose a hybrid scene flow approach. We recognize that regression learning is hard, while correspondence learning is much easier. Thus, we omit the regression part and train a pure correspondence model that is focused only on learning point feature representation. It enables the network to be trained on much less training data compared to other learning-based methods. Then, in the inference phase, instead of using refinement regression with another network component or optimizing the entire flow from scratch, we directly optimize the residual flow refinement for the scene at hand. The initial correspondence-based flow serves as a good starting point for the optimization process, leading to an accurate flow prediction with a shorter convergence time. Here is an illustration of our initial correspondence-based flow. This flow is confined to the convex combination of target points, which may not explain completely the motion between the point clouds. Moreover, there may be errors in the initial flow due to point occlusions and wrong point matches. Thus, we optimized the residual flow refinement component according to the following self-supervised losses. The first one is a distance loss, requiring each warped source point, shown in pink, to have a nearby target point depicted in green. The second term is a smoothness loss, demanding a similar flow for nearby source points. The smoothness loss assists in fixing flow inaccuracies, while the distance loss uses the target points as anchors to keep the translated source points close to the underlying object's surface. This optimization process results in a smooth and consistent flow field between the point clouds. Here, the flow before and after refinement is shown in pink and blue, respectively. The refined flow better covers the target point cloud. It also breaches the convex hull of the given target points and enables computing the correct flow for source points whose target is missing. The resulting flow prediction is similar to the ground truth motion between the point clouds, as shown in purple. Let's see a visual comparison for a scene from the Kitty benchmark, where the source point cloud is in red and the target is in green. This is the result of float, a popular synflow method that uses the joint learning of correspondence and refinement approach. The warped point cloud by float, depicted in blue, is noisy, and the structure of objects within the scene is compromised. In contrast, Scoop produces a coherent flow field across neighboring points, preserves their local geometry, and accurately predicts the scene flow. Additionally, our method is robust and can handle various challenging cases, such as varying point density, repetitive structures, and objects with different motion directions, such as the car and the pole, or elements with different geometry and size, such as the pole and the facade. Another aspect of our method is its balance between performance and time. This graph shows the flow error on the Kitty dataset versus the inference time in a logarithmic scale. Network-only methods tend to be fast, but with limited accuracy. On the other hand, using an optimization-only approach results in a lower error, but it takes a long time. In contrast, our method offers a new working point. It achieves an error reduction of more than 50% over the network-based models and has almost an order of magnitude shorter inference time compared to the optimization-only method neural prior. In addition, Scoop enables various balances between the flow prediction performance and the inference time. By reducing the number of refinement optimization steps, we can shorten the processing time and get a similar working point to that of the network-only models. On the other hand, if we are allowed to increase the inference time, the flow estimation error is further reduced. Thus, our method bridges the trade-off gap between the existing synflow methods. To summarize, we propose Scoop, a new method for synflow estimation from 3D point clouds. In contrast to previous work, we exclude any flow regression learning and instead take a hybrid approach of pure correspondence learning and direct refinement optimization. Scoop achieves state-of-the-art results while using a fraction of the training data. It has a substantial lower error compared to network-only methods and a much shorter inference time than optimization-only techniques. Our code is publicly available. Please see our paper for more details and results. Thank you.